Here's some non-homogeneous differential equations that I want to solve. And what I can see in this case is what I have here on the right-hand side, the non-homogeneous part, is not one of our recognizable functions that we can guess the particular solution for. I don't know what derivatives would end up giving me secant. Same way here, even though this involves e and x cubed, that x cubed in the denominator, I don't know how to take combinations that are going to somehow give me that. If you can think of a way to do that, then that's what you do. You can just guess a particular solution. But when we have something over here that's not one of our basic functions that we use undetermined coefficients for, we use the method of variation of parameters. In that method, we generate a particular solution by integrating, well, by this formula, minus y1 integral y2 r of x, where y1 and y2 are solutions to the homogeneous, and the r is this right-hand side non-homogeneous part. And that's divided by the Wronskian of y1 and y2. And then you just switch to y1 and y2, and you get y2, y1 r divided by the Wronskian. And so just like in the undetermined coefficients problem, the first thing you need to do is find the homogeneous, because here I need the y1 and y2. So I won't work all these out, but let's look at this first one, for example. The homogeneous solution comes from this characteristic equation. And I know that that's going to give me r equal plus or minus I. So that the homogeneous solution is constant times cosine x constant sine x. And that's my y1 and my y2. So the Wronskian is cosine minus sine. That's the derivative of cosine. And then here's sine. And then the derivative of sine is cosine. And so I get cosine squared minus a minus sine squared. Well, that's cosine squared plus sine squared is going to be 1. So that works nice when you have that form, because the Wronskian of those gives you 1, which doesn't add anything too complicated at all to your integral. So my integrals that I have to calculate is y2, which the way I've got these listed, I'm using cosine as y1 and sine as y2. So I've got y2, which is sine, times secant, and then that's divided by 1 dx. And so this being trig functions, I'm going to rewrite this as sine. The secant is really 1 over cosine. So that's tangent. And tangent is one of them. I know how to integrate every trig function, or at least there's basic formulas for them. I may not remember them. But tangent ends up being minus natural log absolute value cosine, or your other option is positive natural log of secant. Different ways of writing it, but this is one way to write that. Plus a constant, but we'll use our constant of 0 here. And then the other integral that I'm going to have is put the y1 in there with secant. Well, that one works out real nice, because cosine times secant over 1, well, secant is 1 over cosine. So that's just going to be cosine over cosine. You just get the integral of 1. And so when you integrate that, you get x. And so now I plug back into my formula up here. And so here's my particular solution. It's y1, which is cosine, and it was negative, but then there's a negative here, so the two negatives are going to go away, times what I got from the integral, absolute value cosine x, and then y2, which is sine, times what I got from the integral. There's your particular solution. Here's your homogeneous solution. So you just add those two together to get the general solution. And again, if you were given particular initial conditions, you could figure out these constants by plugging in the x and figuring out what the y would be. Like I said, these aren't much different. That one has, you start, I'm not going to work it all the way out, but at least get it started. That factors as r minus 1 squared. That gives you r equal 1 twice. And so my homogeneous solution here is going to be c1 e to the x plus c2x e to the x, because of that duplicated root there. And so now I get y1 and y2 are e to the x and x e to the x. So the way this one works out okay, because remember I'm going to be integrating. I'm going to have my y1s out here, so that's e to the x, and then I have x e to the x times, it's this one I'm doing, e to the x over x divided by the Wronskian. Well, the Wronskian here doesn't work out quite as nice in the previous one, but here I've got e to the x and its derivative. Then I've got x e to the x, and its derivative is a product rule. It's going to be 1 times e to the x plus x e to the x, using the product rule on that. But it works out okay. It gives me at least what I need, turns out. So here I'm going to have e to the x times e to the x plus x e to the x. Then I'm going to subtract the product this way, which is e to the x times x e to the x. Well, if you look at this carefully, when I distribute, I'm going to get a positive e to the x times x e to the x. This is a minus, so this one and what I get from clearing there will cancel out. I just get e to the x times e to the x, which is e to the 2x. So that's what's down here. But this integral sets up nicely. I'll have, this is supposed to be a minus, so I'll have minus e to the x in front. I've got an x that's going to cancel here in the numerator, and then I'll have e to the x times x is e to the 2x, so it just works out real nice. The other one's even is not quite as nice, but it works out where you just have an e of some kind that you can integrate. And this one's not a whole lot different. It turns out they've got it set up nice to where things cancel out in a similar fashion. So that's variation of parameters. You've got to remember this formula to do it, to be able to do it. And then you hope that these intervals aren't so messy you can't do them. And you never know what you're going to get. Sometimes you have to integrate by parts and things like that. But that's the variation of parameters method.